Okay, hey friends, we are going to look at this together. You also, if you prefer, can watch Liberty's video. It won't follow these notes exactly though, so it's kind of up to you, whatever you want to do. But for timeline's sake, we're going to go ahead and do this even though I am A for absent. We're going to learn about differential equations and slope fields. We're going to determine if each function is a solution to this differential equation. All a differential equation means is that you can find the derivative. One thing that'll happen to us is it'll be a mix of x's and y's, which hasn't been the case because they're not necessarily functions. They're not y in terms of x. Sometimes they are, sometimes they aren't. So since this equation requires us to have the second derivative and then subtract the original, we need to find the second derivative. So in the first example, my first derivative, because the line card is real, would be cosine, and my second would be negative sine x. So I'm going to go ahead and put those into that equation. So if I have y prime minus y, and I'm trying to see if it equals 0 or not, I'm going to go ahead and put in my negative sine x, and then subtract my original y, which was sine x, and see if it's equal to 0. These don't cancel, however. I get negative 2 sine x, and that does not equal 0. So the answer to this one is no. That is not considered a solution, meaning it doesn't make that statement true. So in the second two, which are actually really similar, one is 4e to the negative x, and this second one is ce to the negative x, which is just more general, saying, hey, what happens if you have a constant in front? So let's find the pieces we need. Here, the 4 is just a constant out in front, like a coefficient. So the derivative of e to the negative x would be an e to the negative x, and then I would have to chain on the derivative of this, which would be a negative 1. So ultimately, I end up here. And then for my second derivative, I would do the same thing. I would get e to the negative x. I'd chain on a negative 1, which would eliminate my negative, and I would kind of circle back to having what I had initially. So if I go to my equation and I do the second derivative minus the original function, I'm taking something away from itself. And so yes, that is a solution to that differential equation. And in the last one, we're saying, did that work because it was a 4 or does it work all the time? So in this case, I would have, again, this would turn into e to the negative x, and I'd be chaining on a negative 1. So I get negative of whatever that constant is times e to the negative x. Second derivative, it circles back to being positive because I would be taking my e to the negative x and multiplying it by its derivative of negative 1, which would change the negative back to positive. So if I take my second derivative and I subtract my original equation, which is what this statement says, will I get 0? That is the question. And because they're identical, that is a yes. So that's kind of one of the concepts we want to be able to do. Now, here it's giving us a differential equation right here. And we are going to verify, so kind of prove that this is a solution. And then our second task is going to be to find the particular solution determined by the initial condition y equals 2 when x equals negative 3. Let's just tackle one thing at a time. First, we're going to decide, I should say verify. So we already know that it's a yes from what we did up above, but we have to actually go through the process. So if this is my y, I have cx to the third. Now, this is not an e, so we're using the power rule. So my y prime is going to be 3cx to the second, and this equation that they're giving us doesn't require a second derivative, so I'm not going to do it. So what I have in general, because the first one's just talking about in general, I'm going to have an x, I'm following along here, and then where there was a y prime, I'm going to put in the 3cx squared that I just found. Then I'm subtracting this 3, multiplying it by y, which was the cx to the third. And I'm checking to see if it's 0. These will multiply to become 3cx cubed, and then I'm subtracting 3cx cubed. So the answer is, yeah, I did. Well, I mean, we already knew it was a yes because it says to verify. So what this is kind of doing is this is going to be sort of the proof of that. You're showing that it is indeed true. And so that's all they wanted you to do. In the second half, when it says then find the particular solution determined by the initial condition. It's really asking you to find C. So let's go ahead and do that. We have y equals c, x to the third. They are telling us that when x is -3, y is 2. So I'm putting a 2 in for y and a -3 in for x. So this turns into a 2 equals c times -27 because of math. And then I'm going to go ahead and just solve for c. So my c value is 2 over -27. So particular solution just means go back to the equation, and instead of using a general C for coefficient or constant, go ahead and put in the number you found that works for that specific condition. And there you have it, my friends. That is what they were asking for right there. Okay, now let's talk about slope fields. Slope fields are not complicated, but without a doubt, they are tedious. So we are literally going to be plotting the slope at sometimes a couple points and sometimes a lot of points. So here we go. Sketch a slope field for the differential equation. This guy, oopsies, writing with a highlighter, not okay. Let's try that again. Teaching is hard. For the points -1, 1, 0, 1, and 1, 1. So -1, 1 is going to be here, 0, 1, and then 1, 1. That is not actually the calculus, my friends, but what we're going to do is exactly what it says. We are going to calculate the slope at each of those points, keeping in mind that y prime from our equation is slope. Y prime represents slope from the beginning of the year. So in each problem, I'm going to take my x value, subtract my y value, and then what I get is the slope of the graph at that point. So what I do when I'm doing a slope field is I go to that point, -1, 1, and I estimate a line that would be going from here down to over 1. So I'd get something like this, and you do just like a little hash line there that has a slope of -2 at that spot. Now the slope at this point, I'm going to take my x, subtract my y, and get -1. So at the point 0, 1, I'm going to have a slope, but it's going of -1. So it's going to be still sloping downward, but not as steeply as the first. Doesn't have to be perfect, but it has to be like a reasonable, good estimate. And in the third instance, I'm going to be finding the slope at 1, 1. So I'll be taking my x minus my y, and I get 0. I love 0 because when I'm doing slope fields, it's one of the easiest ones to know for sure because it's going to be horizontal. And then when I'm finding like information about the graphs in the slope fields, I kind of try to look for the zeros because they're usually good spots to just get information from. So that is how you build a slope field. We did 3 points. You're usually going to be asked, if you have to do it by hand, to do maybe 9, possibly up to 16. So I'm going to choke my way through this video just to prove that nothing has changed over the years. So one of the things that's common on the AP test would be either matching, more so than creating a slope field. You might have to do a bit of a slope field in a FRQ, but in terms of multiple choice, you're going to be obviously just looking at it and gathering some information. So here we're going to match. So what we're given are 3 differential equations, 3 derivatives, and we're going to be trying to figure out which one goes with what. Some of the things that I like to look for, like I said earlier, I like to look for places where my slope has a value of 0. So in this graph, that's where my zeros are. And in this graph, my zeros are going this way. That's where my, those are the points that have a slope of 0 because they have horizontal. And this one, it's a little hard to see, but it's all the points on the y-axis. Okay. So what I'm going to do is kind of look and say here, like at x equals 0, because these are all on the y-axis, they're all 0. Y prime equals 0. Okay, so when I look through my options, at x equals 0, there is not a guarantee in this problem, or excuse me, in this option, that I would get a y prime of 0. Here, if x is 0, I'm guaranteed that my derivative is going to be 0. So that is going to be the one that matches with A. Now I can check other places. Like I can check, well, what about if x is 2? Well, then at that spot, the derivative should also be 2. So when x is 2, so it'd be right here, are all of these derivatives potentially positive 2? Sure are. And if I wanted to check what if x is negative 1, keep in mind all the x's that are negative 1 are right here. They would all have a slope of negative 1. And if you look at those hash lines or slope markings, that is true as well. So that one's going to match. All right, so we've got A matched up. Here, like this point is at 1, negative 1. This point is at 2, negative 2. And so they're opposites. So if I look through my options, over here, if x is 2 and y is negative 2, they do indeed make 0. Same with 1, negative 1. Even back here, I'm at negative 2, positive 2. Because the x and y are opposite, they will indeed add up to be 0, guaranteeing that my slope at those places would be 0. So this one's going to match with B. It would be true if we went around, to the others. Let's say we went to the point 2, 1. At the point 2, 1, 2 plus 1 would give us 3. So at that spot, sorry, these are going by ones. So at that spot, you have a fairly steep slope, but that's because it's a slope of 3 going up from left to right. Obviously, this one is C, but let's at least talk about that. Here we have zeros when y is 0. When the y value is 0, that's where our zeros are in the slope field. What about when the y is 1? Well, then the slope of every single spot along that line is 1. What if y is negative 1? Well, now we're down here, and these are all going to go at about a negative 1 slant. So in this case, the slope of each one is equal to its y value, and that's how we match those up. So slope fields just take a little thinking and a lot of kind of going point by point. And I just like to use the zeros to help match because they're just easier for me to think through than different numbers. Okay, so this says to sketch the slope field for a differential equation. And this is a monster because it gives you this humongous thing. So I don't expect you to draw it. I left my answers on here and my completed one so that I wouldn't take up your whole night plugging numbers in. But understand that what I did was at any given point, I literally plugged them into this equation and took 2 times the x plus the y. And then I would just put what I got. And keep in mind that these values are representing the slope at each point. So when I did this first one at 0, 0, I ended up with a slope of 0. So my little hash line is not slanting, it's horizontal. Here, when I plugged in 1, 1 and did 2 times 1 plus 1 from this equation, I got 3. So that's going to be the slope at 1, 1. So when I went to 1, 1, I tried my best to do like an up 3 over 1 kind of a slant. Okay, so you hammer out a whole bunch of these. It's very unpleasant, but it's not very complicated. And then it says, and this is the reason I wanted to have the slopes on there for you. It says use the slope field, and this is something you will be asked to do, to sketch the solution that passes through the point 1, 1. So when they give you a point 1, 1, you plop yourself down an actual value, and now it's kind of just like a force field. You literally have to follow those hash lines because they're representing the slope of the curve. So since these are all sloping up, so is the curve. Since this is a 0, I know it's going to change direction there. And then from my good old yellow sheet. And then over here, this has to follow. It's almost like you're following through, the invisible force field, except it's visible because you can see where all of those hash lines are. So hopefully that'll help you out. Now you can see that there's slope fields on the bottom as well, but the point they gave us, 1, 1, is up on the top of the graph, or excuse me, top of the coordinate paper. So since this is a 0 at 0, 0, it has to change direction. So there might be something going on below it. We just don't know because we weren't given a point on the bottom half to work with. I think that's the grand finale. So I hope you have enough information with that to get started. I am going to be back tomorrow, and we are going to actually learn something else. Ooh, also potluck. But it's going to build on this a little bit, so we won't go back and reteach this. So hopefully you watch this very enthralling video and can complete your homework relatively easily. See you soon, guys. Bye.